In episode 45, titled Transit Gateways, Hub Routing Without Spaghetti Networks, the conversation starts with a familiar pain point that shows up quickly as cloud environments grow: too many direct connections and not enough structure. Transit gateways are presented as central routing hubs that bring order to that sprawl by creating a single, intentional place where networks interconnect. Instead of every network forming ad hoc peerings with every other network, the transit gateway becomes the common meeting point. This model reduces complexity, clarifies ownership, and makes routing behavior easier to reason about under pressure. For the exam, the key idea is that transit gateways are not just bigger routers, but architectural tools that enforce hub and spoke design discipline. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A defining feature of a transit gateway is that it connects many networks using a single attachment model rather than unique pairwise connections. Each network, such as a virtual private cloud or virtual network, attaches once to the gateway, and the gateway handles forwarding between them according to policy. This approach scales far better than direct peering because adding a new network does not require touching every existing connection. Instead, the new network attaches to the hub and inherits routing behavior based on defined tables and propagation rules. The attachment model also clarifies responsibility because teams know where to request connectivity changes and where to enforce controls. On the exam, descriptions of many networks connected through one hub are strong indicators that a transit gateway pattern is being tested. One of the biggest advantages of a transit gateway is how it simplifies peering through hub and spoke routing rather than mesh designs. In a mesh, every network peers with every other network, creating exponential growth in connections and configuration effort. That complexity often leads to inconsistent routes, overlapping address space surprises, and troubleshooting nightmares that feel more like archaeology than engineering. Hub and spoke routing replaces that mesh with a central hub that all spokes connect to, dramatically reducing the number of relationships that must be managed. This simplification also makes intent clearer because traffic flows are expected to pass through the hub unless explicitly designed otherwise. The exam often contrasts messy peering with centralized routing to test whether you recognize when complexity itself is the risk being addressed. Route propagation is the mechanism that allows networks attached to a transit gateway to learn about each other's reachable prefixes in a controlled way. Propagation means that routes from one attachment can be advertised into a route table that other attachments use, enabling connectivity without manual route entry everywhere. Controlled sharing is critical here because not every network should automatically see every other network. The gateway allows you to decide which attachments propagate routes into which tables, giving you fine-grained control over visibility and reachability. This control supports segmentation goals because you can deliberately restrict which environments or domains are aware of each other. On the exam, route propagation questions are usually about intent, not syntax, asking whether you can reason about who should see which routes and why. Isolation is strengthened further through the use of separate route tables per domain, environment, or trust boundary. A transit gateway can maintain multiple route tables, each associated with specific attachments, so that development, testing, and production networks do not automatically interconnect. This separation prevents accidental cross-environment access and reduces the blast radius of misconfigurations. It also aligns with organizational boundaries, where different teams or tenants require strict separation even though they share the same underlying gateway infrastructure. By assigning attachments to specific route tables, you define which paths exist and which do not, rather than relying on informal conventions. The exam often tests whether you understand that centralization does not mean flattening everything into one big network, but rather creating a place where segmentation can be enforced deliberately. A common scenario used to illustrate transit gateways is connecting many virtual private clouds to an on-premises network without building a tangle of tunnels. Instead of each virtual private cloud establishing its own site-to-site connection to the data center, they all attach to the transit gateway. The gateway then maintains a single or limited set of connections to the on-premises environment and routes traffic appropriately. This design reduces operational overhead, simplifies change management, and makes it easier to enforce consistent routing and security controls. It also helps with address planning and troubleshooting because there is one clear ingress and egress point between cloud and on-premises networks. On the exam, when you see many virtual private clouds plus one data center, the transit gateway pattern is usually the intended solution. Another powerful scenario is centralizing inspection through shared security appliances using the transit gateway as the steering point. Instead of deploying firewalls, intrusion detection systems, or inspection tools in every spoke network, traffic can be routed through a shared inspection segment attached to the gateway. This allows consistent enforcement of security policy, logging, and monitoring across environments without duplicating infrastructure. The gateway's route tables determine which traffic is sent to inspection and which can flow directly, giving architects control over inspection scope and performance trade-offs. Centralized inspection also simplifies compliance and incident response because there is a predictable place where traffic is observed. The exam often frames this scenario as a need for consistent inspection across many networks, which is a strong cue for a transit gateway-based design. A significant pitfall is allowing the transit gateway to become a single choke point without adequate redundancy or capacity planning. Because so much traffic flows through the hub, any failure, misconfiguration, or saturation can have wide-ranging impact. High availability designs, multiple attachments, and appropriate scaling are essential to avoid turning architectural elegance into operational fragility. This pitfall is often subtle in exam questions, where a transit gateway is proposed without mention of redundancy, resilience, or failure domains. The correct reasoning is not to reject the gateway outright, but to recognize the need for resilient design around it. When you see a hub pattern, you should automatically think about how it stays available under failure and load, because the hub's importance magnifies its weaknesses. Another common pitfall is route leaks between tenants or environments, which can undermine isolation goals and create serious security incidents. Route leaks occur when routes intended for one domain propagate into another domain's route table, allowing unintended connectivity. This can happen through misconfigured propagation settings, overly broad route tables, or unclear ownership of attachments and policies. In multi-tenant or multi-environment designs, a single leak can expose sensitive systems or allow lateral movement across boundaries that were assumed to be isolated. The exam often tests this by describing unexpected reachability or cross-environment access and asking what went wrong. Recognizing that central routing increases the importance of governance and careful propagation control is key to choosing and securing this pattern. There are quick wins that make transit gateway deployments more manageable, starting with clearly defining attachments, tags, and ownership. Each attachment should have a documented purpose, clear owner, and consistent tagging that reflects environment, application, and trust level. This clarity makes it easier to reason about routing behavior and to audit changes over time. Ownership matters because routing decisions affect multiple teams, and ambiguity leads to accidental changes that ripple outward. Tags also support automation and monitoring, helping teams enforce standards without relying on tribal knowledge. On the exam, these operational details often appear indirectly, but they support answers that emphasize governance alongside technical design. Monitoring is essential to ensure the transit gateway behaves as intended, especially for detecting asymmetric routing and unexpected propagation. Asymmetric routing occurs when traffic takes one path outbound and a different path inbound, which can break stateful inspection and complicate troubleshooting. Unexpected propagation shows up when routes appear in places they should not, often as a result of configuration drift or misunderstood defaults. Monitoring tools that visualize route tables, propagation status, and traffic flows help catch these issues early. Logs and metrics from the gateway can also reveal traffic patterns that suggest misconfiguration or misuse. The exam tends to reward answers that include monitoring as a validation step, not just a reactive measure after something breaks. A useful memory anchor for transit gateways is hub, tables, propagation, inspection, governance, because it captures the moving parts that define the pattern. Hub reminds you that the gateway is the central point of connectivity. Tables and propagation remind you that routing behavior is intentional and controlled, not automatic. Inspection highlights the gateway's role in steering traffic through shared security controls when needed. Governance ties it all together by emphasizing ownership, policy, and oversight as essential companions to technical capability. When you can recall and explain this anchor, you can usually reconstruct the logic needed to answer exam questions about centralized routing. To apply this understanding, imagine being asked to design routes for 3 connected networks with different trust levels. You would attach each network to the transit gateway and decide which route tables they associate with based on who should talk to whom. You would enable propagation only where necessary, ensuring that lower trust networks do not automatically learn routes to higher trust networks. If inspection is required, you would steer traffic through a shared security segment rather than allowing direct spoke-to-spoke paths. This mental exercise mirrors the exam's expectation that you can reason through routing intent, not just identify components by name. To close episode 45, titled Transit Gateways, Hub Routing Without Spaghetti Networks, bring the focus back to why this pattern exists and how it is secured. Transit gateways provide a scalable way to connect many networks through a central hub, avoiding the complexity and fragility of mesh designs. They rely on attachments, route tables, and controlled propagation to enforce connectivity and isolation, while also enabling scenarios like shared inspection and simplified on-premises integration. The risks come from centralization itself, including single choke points and route leaks, which must be addressed through redundancy, monitoring, and governance. Your rehearsal assignment is to narrate one route table decision, explaining why a route is present or absent and what policy it enforces, because that narration demonstrates the level of architectural understanding the exam is testing. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.